and who are talking. Remember last time I defined what is the cycle type of a permutation. So let me recall that definition. So we have a permutation sigma. And what is the cycle type? Of sigma. These I have denoted by mu sigma. And what is mu sigma? Mu sigma is a tuple, n tuple, mu1, mu2, mu_n. So that in a canonical decomposition, of sigma, mu1 number of fixed points come. So I will just write here 1, 1, 1, that is one cycle. How many times it comes? mu1 times. Then transpositions, that is 2, 2, 2. So there are mu2 transpositions. 3 cycles, they are mu3 times, and so on. And mu_n, that is n cycles, mu_n times. So altogether we have n elements, and these are mu1 plus, so I write 1 times mu1, 2 times mu2, and 3 times mu3, and so on. So you get a partition of n. So this is a partition of n. This is one partition, but there may be different partition, a different partition. And so you know how to compute the partition. So I have computed some by hand. I think I will write few of them. 0, 1, 1, 1, 2, 2, 3, 3, 4, 5, 5, 7, 6, 11, 7, 15, 8, 22, 9, 30, 10, 42. So what this table says, if this is n, this is the number of partitions, Pn. And as you know, there is no formula till today for Pn. Anyway, that is a different issue. That was just to show, but this requires little patience to compute it, but it is not a bad idea to compute. All right. And we have seen the last assertion, we have seen that sigma, if sigma and sigma prime are two permutations, then sigma and sigma prime are conjugates in Sn, that is equivalent to saying they are of the same cycle type. And this means the tuples are equal, right? And conjugate means, you know, that means sigma prime is some tau sigma tau inverse, where tau is a permutation. So now if I want to compute a conjugacy class of a permutation, then I have to count how many tuples are, how many participants are there, how many partitions are there. So that is what. Now, so I will want to compute the partition. I want to compute the cardinality of the conjugacy class. So that is my aim. I want to compute. What do you want to compute? To compute, I will write to compute cardinality of the conjugacy class. I think we were denoting like this. This is the conjugacy class. Class of sigma, which is by definition This is the set of all like this: sigma, tau, sigma, tau inverse, as tau varies in Sn. How many conjugates elements are there? All right. If I want to compute the conjugacy class, I will compute the stabilizer and the index of stabilizer, because I know by orbit stabilizer theorem, this cardinality, this conjugacy class is the orbit of sigma under the conjugation operation on Sn. So this C sigma is the orbit of the operation of the conjugacy operation of the group Sn on Sn. The operation, it's clear now. It's a conjugacy operation. We have seen in general conjugacy and operation of any group. And what are the stabilizers? So isotropy at sigma is equal to centralizer of sigma. This is by definition all those tau in Sn, so that sigma equal to tau sigma tau inverse. So this is equivalent to saying sigma commutes with those taus which commutes with sigma. That is isotropy group at sigma. And we know the index of the isotropy is sigma. This equal to cardinality of the orbit. This we know. And strictly speaking, I wanted also to write S C suffix Sn sigma. But these I have abbreviated by C sigma. Because there are two groups now I want to mix up. So then I will write more precisely. So our problem is to compute this. Therefore, we will compute this. And if I want to compute this, I want to compute the cardinality of Z sigma. Why am I writing alpha? This is sigma. This is what I want to compute. All right. And you may be knowing that this group action is a very effective tool for computing the cardinalities. All right. So how do I compute this? So before I compute it, I just want to make one remark here about this cycle type. So hold on, this I will write. This we will start computing next time. But I want to write one remark here about cycle type. So sigma, nu of sigma is this nu1, nu2, nu_n. This is a cycle type of sigma. This is called cycle type because it is arising from that canonical cycle decomposition of sigma. Now, what was canonical cycle decomposition? You write sigma as a product of cycles. And now we write little carefully. Now, if there are sigma 1, this is one cycle. No, not one cycle, but they may appear several of them. So I will write only sigma 1 because I don't want to make complicated notation. So this will appear, one cycle will appear. So how many times? Nu1 times. They're all one cycles. Then 2 cycles will appear so many times, nu2 times. 3 cycles will appear nu3 times, and so on. N cycles will appear nu_n times. This is actually the finer way of writing canonical cycle decomposition. And you see, you are counting them. How many of them? The new one, these are new two, and so on. So what will be the class equation? So what I'm asking you the following. If I take the subgroup generated by sigma and ask for this is operating on the set 1 to n, this is a subgroup of Sn. This is my notation for subgroup of Sn generated by sigma. So that means what? What are the elements of this H sigma? They are identity. It's a cyclic group. Identity, then sigma square, and so on. When the power of sigma becomes identity, just one before that. So order sigma minus 1. This is the subgroup. The subgroup has order equal to order of sigma. All right. So what is the class equation? The new one will be the number of fixed points. All right. So on the other hand, the set which are operating is 1 to n. So n will be equal to mu 1. This mu 1 is the fixed points of sigma, number of fixed points of sigma on the set 1 to n. Then mu 2, this is the number of orbits of sigma of cardinality 2, because there are 2 cycles. Then mu 3 will be the number of orbits of cardinality 3, and so on. And mu 1 will be number of orbits of sigma of cardinality n. Is that clear? So this is a class equation for this action. All right. So this might be useful for some calculation. So now let us come back to our aim is to calculate what is the cardinality of this centralizer of sigma. All right. So what will this note that these elements of the centralizers are the conjugates which are equal to sigma. And we know if I want to know if somebody is the orbit of sigma, what is the orbit, how the orbit we can write down for the conjugate of sigma. So if this, so that means I have to understand what happens to the cycles. So suppose I have an I cycle or n cycle look like this. Again, I should not write the commas. This is what cycle looks like, typical cycle. And what happens when I apply tau? I told you last time, the cycle corresponding to this will be very easy. It is tau x1, tau x2. I should write bracket here, but sometimes tau xn. This is the orbit. Now this is the cycle. If this is a cycle of one cycle appearing in the cycle decomposition, then the corresponding cycle which appears is this. So it is, what does it do? This tau will permute the element in the cycle. Right? That is what I want to observe. All right. Now what happens? I'm going to give you a map from, see, I want to compute Z sigma. So I am going to give you a map from Z sigma. So before I write it, I will create some notation. So let us call big script X I. This is equal to set of all orbits of sigma of cardinality I. So for example, script x1 will be just the fixed points. Fixed points of sigma. Capital script x2 will be just two orbits with two cardinality. So they will look like this. So this set will look like x1, x2, and some more. And this one, how do you write in the cycle decomposition? Writing x1, x2. Similarly, the others. So the notation is clear. And what we observe, if I make a conjugation, if you have a cycle, that will become a cycle. So that means the orbit corresponding to this cycle will get some other orbit of the same cardinality. So that simply means that each tau if I take the permutations on this capital Xi, I will write first and then we will explain. I will explain the notation. So where did I write? So if I take the product of these sets, this product is from I equal to 1 to n. Obviously, cardinalities can be from 1 to n only because sigma is operating on 1 to n. And Z sigma is here. And this, I want to define this homomorphism. First, I will define the map. This is not alpha, this is sigma. What is the map? The element here is conjugate of sigma by tau. And just now we saw if these are the orbits of sigma of cardinality I, and this guy will permute the orbits among themselves of the same cardinality. That means it gives me a permutation. So that is that map phi. So this is going to be, so it will be an element in Sn. So I don't know what to write. If I want to write, I will write rho 1, rho n, where rho I is a map from this xi to xi, and this map is obviously bijective. And one orbit here, if I will only write the orbit by x, this x has cardinality I, that will go to t of x, tau of x. Then we have observed that is also an orbit of the same cardinality. So the cardinality of tau x is also equal to I. This cardinality x equal to I. So that is the map. And I say this map is a group homomorphism. So I will not check that. Whatever I don't check, that you check it at home. If you have difficulty, you ask me the next day or in the tutorials. This is a row, this phi is a group. So why do I call it phi? Let us call it rho only. Rho is a group homomorphism. This is a group. This is also group. It's a product group. It's a big group. So this is a group homomorphism. Now, my aim is to compute this, and this cardinality I know. What is the cardinality of this group? So cardinality of this group is how much? Can somebody tell me? Come on. What is this cardinality? Please. Now I cannot raise my by names, no? All right, so Ishan is there. Hello, Ishan. See? Hello, Tithi. Tithi.
Yes, sir, I am there, but I don't know.
You don't know. You don't know what is the cardinality of script xi. What is xi? How many elements xi has? I said no. How many elements xi has? Xi is the number of orbits of cardinality 2. Not 2. X2 is, for example, number of orbits of cardinality 2. And then our notation says nu 2. I've written here exactly. Number of orbits of sigma of cardinality 2. Now we can tell what is the cardinality of S of x2, for example.
Some mu 2 factorial.
Nu 2 factorial. Very good. And in general, cardinality of S of capital script xi, nu I factorial. And the product. So this product of the cardinality is nu 1 factorial, nu 2 factorial, etc., nu n factorial. Ishan, do you agree? All right, so that is the cardinality I know for sure.
Yes, sir.
So if I know the kernel of this map, that will help us. So I'm going to tell you what is the kernel. Because first of all, note that this map is surjective. So another thing to note is rho is surjective. Because these orbits corresponds to the cycles, and therefore I can recover my whatever the map it is, the conjugate, the tau I can recover. Therefore, check formally it is surjective. That's not difficult again. All right. The third thing importantly, I want to know what is the kernel. Kernel of rho. If I know this, then I know by Nitin's lecture also somebody was saying first isomorphism theorem for groups or whatever, that this modulo, the kernel will be isomorphic to this group, and therefore I will know the index. And therefore, if I want to know the cardinality, if I know the kernel precisely, and if I know the cardinality of the kernel also, then I will know cardinality of Z sigma. So I will tell you what is the kernel. The kernel of rho is precisely the product sigma 1 cross sigma 2. Now again I will leave it like that. See here, what did we decide? Here, look at the canonical decomposition of sigma. That few 1 cycles will come. How many mu 1? Few 2 cycles will come. How many? Mu 2. Few 3 cycles will come. How many? Mu 3 and so on. So I'm taking those and generating the subgroup individually. So H sigma 1 will come few times. This will be mu 1 times. So actually, strictly speaking, I should write different another notation, no? So, but that will make complicated. See here, if I start making complicated nu 1 1, then nu 1 2, and so on, and nu 2 1, and so on, so that will be the notation. So if you want, we can write like that. So I will erase this and show you what one should write if one wants to write very precisely. So this product will go from I equal to 1. Now again, index I is a problem. So it will go from K equal to 1 to K1 H sigma 1 K. So they are all 1 cycles. They are all 1 cycles, and how many? Nu 1 times. So this is nu 1. cross product. Now K equal to 1 to nu 2 H sigma 2K. There are two cycles, that transposition, how many nu 2, and so on. Cross product K is equal to 1 to nu N H sigma N K. Is it clear?
Sir, can you please explain this? How kernel of rho is equals to this?
Yes, I will explain that. So what does this? What does this? This is a part of that sigma. So for example, I will explain this one, and then similarly any component. So what do you do here? This is sigma 2. This is a 2 cycle appearing in this sigma. So let me write like this. So sigma we have written as a product, right? Sigma 1 appearing few times, and that is how I have clubbed it here. Sigma 2 appearing few times, that is what I have clubbed it here. And sigma n appearing few times, that I have clubbed it here. And this is 1 cycle, this is 2 cycle, this is n cycle. There are n new 1 of them, these are new 2 of them, these are this and that. Now, what does this corresponds to? This corresponds to the orbits of sigma of cardinality 2. So they look like this, x1, x2. And what do what are they? This is the tau. This is not the correct way I have written. This is the tau. Tau is mapping to that. See, the elements of Z sigma are the taus which commute with sigma. So I am mapping tau to this element. And how are these elements? See, there this is right. So now what will tau do to this? The tau will give me the orbit tau of x1, tau of x2. This will be the orbit. This will be actually the 2 cycle appearing in this conjugation. Is that clear? Who was asking me? Sonakshi?
Yes, sir.
Isn't that the definition we have made it here? This tau is going to this. So this cycle, see, the cycles are more precise than saying the orbits because it has decided the order also, which goes to which and so on. If I say the orbit is a set that you don't know who is going to which element under sigma. But here I know under sigma, this x1 is going to x2 and x2 is going to x1. So the cycles in the canonical decomposition is more finer, it gives more finer information than the orbits. So this cycle goes to this cycle. But now this tau x1 and x2, we don't know which is x1 and which is x2. So particularly this problem will increase when you take suppose R cycle like this, R cycle is like this, and it is going to this cycle. Tau x1 to comma, so tau xr. Now here only thing we know, they are shuffled according to this permutation tau. So we don't know who is who. Here we know x1 is going under sigma to this, xr minus 1 going under sigma to xr, and xr under sigma is going to x1 back. Here they are shuffled only. But it is a cycle. Yes? Please ask question. This is very important point. Right? So therefore it shuffles. The orbits got shuffled to some other orbit. But within that capital X I said. So therefore I said a permutation. So this gave me a permutation. This row map gives a permutation on these orbits, capital X's. And now what is the kernel I'm saying? If you take this permutation, these cycles, they are only permuting. And where will they go? as orbits, they will go to same. Isn't this set same as this set? So therefore the orbits are going to the same. So therefore these guys are in the kernel. All right.
But H of sigma 1k is the subgroup generated by sigma 1k, right?
See, remember what did I write for capital Xi? But you see that the tau, this shuffling, even what we have mapped is one orbit of sigma of cardinality 2 has gone to the some other orbit. That may be here somewhere. This cycle is maybe different.
Yes, sir. But I'm not getting this point that how kernel of rho is equals to the subgroup generated by all these sigmas.
Okay. Now tell me where, suppose we started this orbit. Where does it go? Orbit. I'm not saying the cycle now. Because here these capital Xi's are the orbit. So
Yes, sir.
in capital Xi, capital X2 for example, capital X2, I will write down few elements. This is one element, X1, X2. It's orbit. And also it is this another element. So let me write the little bit bigger cardinality so you will know. So suppose I want to write X3. So this is one orbit and that will give me which cycle? It will give me X1, X2, X3. Now suppose the tau was some other permutation. Say tau was say 1, 2. Just I am giving an example. Tau is 1, 2. Now what will be this orbit? That orbit I should, strictly speaking, I should write tau of x1, tau of x2, tau of x3, right? But what will be the cycle? So this is that set. But isn't this set is same as x1, x2, x3?
Yes, sir. Shuffled x1, x2.
It is just shuffled because when I write like this cycle, then I will have to write, what will I have to write? This tau of x2, tau of x1. So I should write this as, this will, tau of x2 will be x2, tau of x1 will be x2, tau of x2 will be x1, and that other one is 6. Now, you see, this cycle is different from this cycle, isn't
Yes,
it?
sir.
But the orbit corresponding to them are equal, isn't it?
Yes, sir.
As I said, so that is the difference. So note that because of this formula, what we have, which is that I wrote no this one. Because of this, the sets are equal,
Yes,
but
sir.
order has been disturbed. So therefore, when I apply that sigma powers, that will not change the orbits, but that will change the cycles.
Okay.
Right? So therefore, now you check that the kernel is precisely this. That is more or less obvious. All right? So
Yes, sir.
suppose you have checked that, then I know what is the cardinality of this kernel. Let us compute the cardinality of the kernel. So this, let us call this subgroup to be H. Then cardinality of H. No, this is subgroup. Let us take this H2. This is, so let us call this as H1 cross H2 cross HN. And now can you know that this is a product group, therefore cardinality of H will be product of cardinalities of HIs. I is from 1 to N. What is cardinality of HI? Each HI is appearing how many times?
Order of sigma 1k.
Why? Very good. But what is the order of sigma 1 I? You mean I? I have written I here. You want to write K? Write K. Doesn't matter. So what is the order of that group? Order of this group?
New I.
And new one will appear many times, no? How many times it will? So this cardinal, first of all, suppose there is only one. Then what is the cardinality of the two cycle subgroup generated by R cycle? What is the cardinality?
R.
Not R. What is the order of R cycle?
So R cycle order is R, right?
Is it R? You may be correct, but you have to be confident enough to say, yes, it is R.
Yes, sir.
It is R. Very good. And how many times that is appearing? New R times. Isn't it?
Yes, sir.
See, how many times this is appearing from 1 to new 2. So that means, and this is 2 cycles. So each one has each one has order 2, and that is appearing new 2 times. So it is 2, 2, 2, 2, new 2 times. That is 2 power new 2. Similarly, if it is R cycle, if you are taking R cycle order is R and it is appearing new R times. So the cardinality of that component will be R new R times. So that is 2R power new R. So this cardinality, therefore, I will write it down here. Cardinality of the kernel is precisely 1 power new 1, 2 power new 2, R power new R, and so on, N power new R, new N. Agreed?
Yes, sir.
But now, therefore, and what is the formula we are getting? Cardinality of Z sigma modulo H. This cardinality I know. This is equal to cardinality on the that side. That is the subjective. So everybody. So this is the cardinality of the product group, permutation group on this capital exercise. I is from 1 to n. And this cardinal product, therefore, I can push that cardinality inside. So this is I equal to 1 to n, cardinality of S of exercise. And orbit, how many orbits are there? They are, what is cardinality of xi, capital Xi? That is nu I. That is what we were assuming. So this is product of new i's. So this is product I is equal to 1 to n new I. Agreed? Yes or no?
Yes, sir.
Not
Sir,
new I,
it's
sorry.
factorial.
Yes, sorry. Good. Sonakshi, you said it. And the other side is this. But the other side cardinality, I know what it is. This is a quotient group. So the cardinality of the quotient group is cardinality of the numerator group divided by cardinality of the down group. And down group, I know the cardinality. We have computed this. What is that? This cardinality, I know. This is 1 power nu 1, 2 power nu 2, and n power nu n. Agreed? Therefore, from here, I know cardinality of the conjugate, the centralizer of sigma, which is equal to nice formula 1 nu 1, 2 nu 2, n nu n times nu 1 factorial, nu 1 factorial, nu 2 factorial, dot, nu n factorial. That is what we wanted. This is the formula I wanted to put. So that is what we have computed. We have computed the cardinality of the centralizer of a permutation. And it is very simple. Now so calculation is so natural. Only thing you have to keep checking what you are writing. And should I stop for a minute and give you a chance to ask me question if you have? Please, this is very important formula. Not many books will give you. Shall I go on? Sonakshi?
Yes, sir.
All right, I will go on. And now we want to, you have seen so far now, what is important is for the calculation, one thing which is important is the signature, and the other thing is what is important is the cycle decomposition. And both the things are very natural definitions we have. But now in the next example, I will tell you some other way to compute the signature. So this is example, and this was the standard. This example is actually used to define signature in many books. So these are called inversions. So the roughly speaking, signature of a permutation is the number of inversions. That was the definition, for example, given in Einstein. But the difficulty there is to prove it is a homomorphism. You check that whether you really understand that proof or what does it consist of. Checking that it is a group homomorphism, it's more tedious, and then that is where he has jumped somewhere. So make sure that we understand. So I will tell you what is the inversion. So we have given a sigma in Sn and a pair I comma j is called an inversion of sigma if I is less than j, but sigma I bigger than sigma j. You see, it changed the sign. Therefore, it is called an inversion. And now, so for example, what is the sign for a transposition? Tau, if tau is a transposition AB, and we have, while writing the transposition, you can always assume like this. If A is bigger, then I will write B first. That doesn't matter in a transposition. So when will it be when will it be a transposition? What are the inversions of this tau then? For example, if I take the pairs A comma A plus J, if I take these pairs where J is from 1 to B minus A, I am assuming this. I can assume this without loss. Now let us look at these pairs. Let us decide whether they are in inversions or not. Right? So what do I have to check? I have to check that what happens to sigma A and sigma of A plus J. And A plus J, J I am taking up to B minus A only. Right? So which is which? Now what is, this is sigma B is here. Sigma B is sigma of A plus J is B minus A. And what do we know about the comparison between sigma A and sigma B? Sigma A is B and sigma B is A, that we know. And now it has reverse. This is bigger, so it has reverse. So this is definitely this j equal to this, definitely is a inversion. And similarly, all other earlier guys, see here, what are the earlier guys, a and a plus 1, for example. So what do you have to compare? You have to compare sigma a and sigma of a plus 1, but a plus 1 is not appearing there because I am assuming b minus a is bigger, let us say. Then what do I know? That is a plus 1 only. And this is b. And because of the assumption that b minus a is bigger, b is still bigger. So therefore this is also inversion. And so on. And you can do this argument till b minus a. So, and exactly those. Other than that, there is no inversion. That please check that. So therefore, number of inversions, actually you can write down all inversions of this. I have written down all of them. J is from 1 to b minus a. So the number of inversions are b minus a. No, I forgot also something. So I forgot the other pairs, the other side. I forgot what happened to the other side. See, here I kept a fixed and this increase. Now I can do the same. I can keep b fixed and then increase this a plus I. And how much can I do that? I is from 1 to b minus a minus 1. So therefore, the number of inversions are this together with this. So how many they are in number? B minus a from here, b minus a minus 1 from here. So b minus a plus b minus a minus 1, which is equal to 2 times b minus a minus 1. That is the number of inversions. And this is odd number. And sign is related to the inversion by this formula. So sign of sigma.
Sir, I have a small question.
Yeah,
That
1 minute.
yes.
I will write the formula and then you can ask me. That is minus 1 power z of sigma, where z of sigma equal to number of inversions. I have to attend the phone and you can ask me. Okay, now you are, so this is the formula I wanted to check. And above I just computed the sign of permutation according to this formula. Yes, now who was that?
Sir, I am Purnashree.
Purnashree, ask me.
Sir, I want to ask that for inversion, can we have to fix an coordinate and we have to change other, right? Means we cannot change both simultaneously.
No, here I could check that because I have a transposition. So in general, writing down in inversions will be not so easy.
Yeah.
See, suppose I take 3 cycles. So this is transposition, so it was easy because I took those points, I took this A and B, assumed A is bigger than B, and then I checked somebody from here and somebody from there, no? Somebody from, once I moved the first coordinate, here I kept the coordinate A fixed, and then I take this point, then I kept this coordinate free and I went back. Right, that was the procedure I adopted here.
Okay.
But this I can do it very well because I know the transposition. So I know one is smaller, the other is bigger, and they are. I can always arrange my transposition so that it starts at the smaller. But supposing I have a 3 cycle, 1, 2, 3. Not 1, 2, 3, but some other 3 cycle. So suppose it is like that. 3, 1, 2. Now it will be difficult to compute how many inversions are there. But this is the number I need, how many inversions are there, and that power minus 1 power, that number is the signature.
Okay.
That is the formula. And
Okay.
once you prove this formula, that is what I am saying. If you prove this formula, then you will get the, if you prove this equality. Proving this equality is not as easy as the way we have computed the sign.
Okay. Okay.
All right. This is what
Yes.
precisely this formula you can find in Herstein. That is his definition actually.
Acha. Acha. Okay.
So I will tell you what the definition he gave the Herstein. So this was Herstein's definition was the following. I will tell you. See what he did was he considered this product of this product is running over 1 less equal to I, strictly less than j, less equal to n, and sigma of I minus sigma of j. You consider this product. Sigma j minus sigma, I wrote the other one. Sigma j, sigma of j minus sigma of I. This product. And now you want to relate this with the product. Of course, the sigma and sigma j are also numbers in between 1 and n. But you want to relate with this. J minus I. And he says they will differ by a sign. And how do you compute that sign? That is minus 1 power z sigma. And whatever that power comes, that you want to define signature. That was the definition. And this looks very complicated definition to me to check that it is a group homomorphism.
Yeah.
All right. So that is what I want to say. You also, I will say, please check this formula, check this formula. And if necessary, look at Einstein. Which was our textbook when I was in IISc second. All right. But this definition, our definition is so very natural. And therefore, we have no problem in taking that into this. So here it doesn't say about orbits, etc. All right, so that I will not check this formula because you can check it each time. And actually later on when I found out that actually there is no, but we need more explanation for that. That is how nature will in a quotient. So this is like quotient definition, but I don't have enough thing now to recall this. I will do it sometime. And this is related to theory of equations. Studying the roots, studying the zeros. That was the main problem in earlier days. The main problem in 17th, 18th century. Study of theory of equations and their zeros and so on. So that I will do it sometime in this course only. But right now our problem is to settle the group N is not is simple for n bigger equal to 5. That is what I am preparing for. All right. So now again back to our preparation. So for example, you can also compute the signs of permutations by using these inversions. Sometimes it is not too bad because you saw in a transposition time it is not too bad. So it depends on a permutation. The difficulty will depend on the permutation. All right. Now let us continue our study preparation for ANs. I'm preparing. So next observation I want to make that is center of this group Sn is trivial. How do we prove this? Anybody has idea how do we prove this? All right. So I will tell you the proof. So what do you want to prove? Center is trivial. So let us analyze what happens if I take a sigma and a and a cycle and a transposition actually. And suppose it commute, suppose the sigma belongs to center, then it will commute with all permutation. It will particularly it will commute with the transposition. So therefore, if I take sigma transposition, sigma inverse, it should again be a sigma, no? That is the meaning that it will commute. Right? And this should happen for all transposition and even more. But what does this formula tells you? You know how to compute this. This is sigma A, sigma B. That is how we know how to compute the conjugate of a permutation. Here, how to compute the conjugate cycles in a conjugate of a permutation. So this is that. And if this has to be this, then sigma A has to be A and sigma B has to be B or the other way. So now if N is at least 3, so if I choose A and B such that this sigma A along with they are distinct elements. They are different, distinct elements. That is possible because N is at least 3. I have given only A and B, and I choose C different, and I want to take that as sigma A. And now I complete it. A goes to C, and then remaining guys you do whatever you want. It doesn't matter. And all right, maybe B also you have to choose. B also you define so that it is different. So this is A, this is B also you can do whatever you want. This is arbitrary and this is also, this is actually defined. This is not, A is not definitely B and not definitely sigma A. Then what do you get? This A is different, this is C, this is whatever D, and how can these be equal to AB? When C and AB and CD should be equal. Only the order, but the order doesn't matter for the transposition. So, and C definitely doesn't belong here. Because B is also different from B. That is why I have chosen these 3 elements distinct. What did I write? Oh. So you choose A, B, and sigma A, call it C, 3 distinct elements. And define now sigma. So that sigma will definitely non-identity and it will never commute with this transposition. So that means no sigma will be in the center other than identity. So we proved that the center of the permutation group is trivial. Okay, the next one is next observation, second. every sigma in Sn is a product of 3 cycles. So not in Sn, I meant An, because we want to study the group An more carefully. An is alternating. That means sign of sigma is even. That means the number of even orbits in sigma is even, because the even orbits gives the negative, and if the sign has to be 1, the number of negatives has to be even. So the way I remember is sigma is in N if and only if the number of even orbits is even. So that means in that our earlier notation, I wanted to make that comment there, so I forgot that. In this case, in this notation, when will that happen? If this is our cycle decomposition cycle type, when will the sign of sigma will be even? That is 1. So sign of sigma equal to 1 if and only if, what in terms of this new cycle type, that is number of even orbits, they are nu2 plus nu4 plus nu. How can I go on up to n nu by 2? This sum should have cardinality even. That means it is 0 mod 2. Actually, this cycle type, why I said this, because cycle type gives a very finer information about the permutation. All right, so let us come back to this observation. How do we prove this? I know every element, every sigma in N is a product of even number of transpositions. So if I prove, so enough to prove, I will use this short form ETPT. That is enough to prove that. If I have 2 cycles, 2 transpositions, and it is a product of 3 cycles. But this is actually, what is this product? If you compute this product, so if it is, what can happen? They are either completely disjoint. I mean, that means A, B, C, D are different, or there will be one element common. 2 element common, that cannot happen, because 2 elements are common. That means CD and AB is the same transposition, and this is the square, which is identity. And identity is, so along with this, so if sigma is not identity, is product of 3 cycles, and if sigma is identity, it is product of 3 cycles but empty product. That is the standard convention one has. No, if you multiply so many numbers over some set, indexed by some set, and if that set is empty, then what is that product? That should be 1. No, this, I think Nitin was talking about this many times in many situations. Anyway, so what is this? So I will consider 2 cases. Either they are A, B, C, they are different. That means they are disjoint, empty, or only one element in common. So I will call B equal to C. I only have to consider these 2 cases. And in this case, what happens when they are completely different? So this is also in this case. In this case, I will write this. So AB, CD, and I will do little bit. So I want to make one element common in that. So AB and then BC and then BC. I inserted BC in between and then CD. They are different. All elements are different. A, B, C, D are different. So what is this? Let us compute this. So how do you compute? You start from this side. So start from C. C goes to D. D is fixed. So C goes to D. D is fixed. So C definitely goes to D. Where do D go? D go to C. So I will write the resultant check. I think that may be better. That will save some time. So I say this product is same as ABC and BCD. Let us check that. Now here, start with B. So here, start with B. B is fixed, so forget it. B goes to C, C goes to B. B goes to C goes to B, and B goes to A. Therefore, so I have to compute this both sides and then check. So where do B goes here? B goes to C, C goes to B. So B is fixed. Not B is fixed. C is going to D under left side, right side. This is RHS. Where do C goes? C goes to D. D is fixed. So C goes to D there. No. Am I confused? I am confused. C goes to D here. So why did I write C goes to B? This is not correct. C goes to D here. RHS I will write. RHS, where do A go, where do B go, where do C go, and where do D go? I will write below. Little slow, but once at least we have to do this. This is RHS. And down I will write LHS. So let us see where A goes. A is fixed here, A goes to B here, so A goes to B under RHS. Here, A is fixed, A is fixed, A is fixed, A goes to B. So B. Where do B go? B goes to C, C goes to B. So B goes to C and C goes to B, so B goes to. Oh, we have, what did we check? A goes to B. So B goes to C and C goes to A. So B goes to A. I will write with the black here. Now B goes. Where do B goes? B is fixed here. B goes to C, C goes to B, and B goes to A. So B goes to A. C, where do C go? C goes to D. D is fixed, so C goes to D here. Here C goes to D. D's don't appear, so C goes to D here. C goes to D here. Where do B go? B goes to C, C goes to B, and B goes to C, so D goes to C. And here, so RHS and this is RHS is correct. No, I have took that left. So C goes to D, D is fixed, so C, oh, again, let us do it from. So RHS first, that is C goes to D, D is fixed, so C is going to, that we have checked. So D, where do D go? D goes to B and B goes to C. So this goes to C, and here B goes to C, C goes to B, B goes to C, so it goes to C. So all are correct. This. So this equality we have checked. And these are three cycles. And B equal to C case, it's more easier because so that means we have to write AB times BC, so CD, BD. And this is same as why do I write this? Okay, this one is same as A, B, D. Let us check again. A goes to B here. Where do A go? A goes to A is fixed here, A goes to B. So that is correct. B goes to D, B goes to D, D is fixed here, so B goes to D. D goes to A, D goes to B, and B goes to A. So that's correct. So both these equalities are correct. Therefore, we have written every even permutation as a product of 3 cycles. That means this group AN is generated by 3 cycles. All right. So in other words, AN is generated by 3 cycles. All right. The next observation, third. I am running out of time, but we can't help. So this here I didn't use. What did I use? N. I didn't use N. Any N is at least 3. Now, if N is at least 4, then the center of AN is also trivial. So let us take sigma in AN, and sigma is not identity. Then I should produce a 3 cycle whose conjugate is not the same 3 cycle. So I want 3 cycle ABC, because 3 cycles are in AN, and I need to produce element in AN, so that this sigma doesn't commute with this. So that means sigma of ABC sigma inverse should not be equal to ABC. This is what I want to produce. I want to produce ABC. And there are 3 elements. This is 3 cycle. So therefore there are 3 elements. And I will choose now ABC. What will I choose? I will choose A, sigma A, and B. 3 distinct elements. Is that enough? I will choose actually 2 elements first, so that sigma A is not equal to B. A sigma A is not A. And B and C different elements. B and C, along with this, these 4 elements I will choose different, distinct. Then I know this side. How to compute this side I know. This is which cycle is this? This is sigma A, sigma B, and sigma C. And I need to check that this 3 cycle is different from ABC. So let us see where it goes. See where it goes. Let me just say where. So if they are equal, their support should be equal. See, all these guys are moving. So therefore, if they are equal, if equality here, then sigma A should belong to this ABC set in particular, because it is moving. And But I have chosen these 4 elements different. Therefore, sigma A is not there in ABC. This is not true. Therefore, this will not be true. Because sigma A is moving here. And you can choose sigma A is given not identity. And this is different. And so on. So even if worst case to us, this is B and this is C, still in this C will go to sigma A and in this C will go to A. All right. So convince yourself that what I wrote is correct. So therefore we noted that the center of the alternating group is also trivial. Now the last statement 4 and then I will stop. 4. Now I will need an at least 5. Then all 3 cycles in AN are conjugates. In AN. So that means what? That is, if I have given 2 3 cycles, ABC and the other one C, D, E, F. These are 2 3 cycles. They are conjugate means I should be able to find, given this 3 cycles, I should be able to find sigma in AN such that ABC or A no comma ABC conjugate by the sigma, this is equal to DEF. So what do you have to solve for? I know this side. This is sigma A, sigma B, sigma C. This I want to be equal to DEF. And I want to define sigma. So I am looking for sigma. All right. So because so this I would say you do it as a homework. If you don't get, we will do it in the tutorials. When you do this, you adopt the same policy. You want to define sigma. And you have to choose n is at least, you have to use the fact that n is at least 5. That will help you to define sigma. So with this I will stop because I don't want to kill the time for the tutorials. So I will stop this presentation, and before I stop I should send you